equator or equatorial plane. This is the orbit. It tells you how it is oriented with respect to that tail. These are those angles. Got it? Can you measure it? If Earth is going like this, or and Sun's this thing, can you measure these angles?
Yes.
You cannot really measure those angles.
No. Because it's in space, we can get that.
Yeah, it's what you have to think about. Orbits are not. If somebody did not study, right, we would look at those are just points. Okay, the plane, the path. What is not abstract in an orbit?
The actual stuff moving around.
What is not abstract here? Only this thing, possibly. Even not this. So how do you see? If you see Earth, can you just see? If you see some other planet, can you just imagine it as being in a plane? What do you see? You just see some point, right? A dot. You see, translating that dot to something so meaningful, something so elaborate. That is what you need to figure out. Okay. So what you can really measure is, you see, how do cocks measure your speed?
They take a relative point.
Huh? Yes. So you can always measure the position. Can they measure your position?
Yes.
So when you're going, right, when you're going like this, somebody sitting here, okay, they flash a radar here, or a LiDAR, okay, that bounces back. They know the speed, and they'll know from speed and what is the time taken. They'll know what is the distance. What is the relation between speed, time taken, and distance? Distance over time is speed. Okay, so they know the speed of light, which is going and hitting and coming back. They know this how much time it's going to take. If you multiply that by time, they'll know your distance. Okay, so when they want to know the speed,
They'll do 2 points.
they'll take 2 points.
Because
They'll
it's
know.
not actually cover that distance.
The speed, yes. You can do exactly same. That was, in fact, all these things were done more for these distance objects. Okay, you've heard about moon bouncing something off of the moon. You can bounce something off of the moon. Okay, and you know what the distance of the moon is. So here, these can be practically measured. R and V. Here R is the position and velocity of an orbiting body with respect to single body. Okay, these can be measured using instrument. Now, how do we translate these to these? That is what we are going to learn next. You see that? Can two orbiting bodies have the same orbit?
No. Or they run into each other.
Huh?
So how do you measure the velocity of Earth relative to the Sun when you're
So
telling
you measure the other way. So if you're going, let's say you have cop's car, right? If you're pointing a radar, there are instruments in your car which will give you, which will tell you whether or not that. That's not relevant. So if you hit a this thing, you know the relative velocity of yourself because that thing is constant. It's like,
which frame are we talking about?
so if you're going in a car, right?
Okay, so I'm in that.
And there's somebody stationary. You can think about, have you guys traveled in a train?
Yes.
Sometimes when the train beside you is moving, do you feel that your train is moving?
No, that's what I feel like it's.
Or even if you're sitting in an airplane, if you see something moving by the side, Do you see? It's like if something is moving, okay, it's relative.
Yes.
If you think the cop's car is where it is when you are moving, you can also think about that as you are where you are. The cop's car is there. Okay. So the relative speed, instead of measuring yourself, if you measure the relative speed of cop's car, you'll know what your speed is.
Okay.
Got it? So you can do that with the sun.
I get that, but like, how does acceleration factor in when we're speeding up the song?
So what you do is you measure. So let's say we are very good with now keeping a track of time, right? So if you keep a path of what, so that's what Kepler and Tycho Brahe did. They kept a track of what was their path around the sun 1 year.
Oh, so yeah, it's like having flight lessons.
Yeah. So then you trace that on this thing to figure out the position and.
Okay, that makes sense.
Okay. So this we have to learn how to. This is what most of the, for example, the U.S. Air Force keeps a track of all the orbiting particles, even small, even centimeter size objects. What they can keep track is, or what they can really measure is R and B. That is translated to these 6 elements, and we'll see how that can be done. Okay, so I'll just get started with this. Or before that, let's do. Just look at right ascension and declination. I think we'll start with this. It'll make things easier. Okay. Right ascension and declination. Now, again, this is O, this is Z, this is X. Sometimes we are going to use this as I, this is Y, this is J, this is K. Okay. Now you have your Earth is here, okay? And let's say your satellite is somewhere here. What is R now? Just think about this as sphere. This thing. Got it? This R would be?
Distance from the center to the.
Yes, exactly. So this is that distance. Okay. And this would be V is here. Got it? You understand latitude and longitude. Everybody understands that?
Yeah.
What is latitude?
Latitude is the.
So longitude, latitude is
Latitude, which one? Longitude.
longitude are lines which run from
Poles.
north to south, poles, but are measured in the east to west. Right? What is 0 degree longitude? Where does it run from? Yes, that's correct.
Yeah.
0 degree longitude. Anybody?
Where is it?
Yes.
Is it in England?
Yes. GMT. You understand GMT? Greenwich.
Meantime?
Greenwich Mean Time is GMT. What is Greenwich?
City?
It's a city in England. So the 0 degree longitude runs,
Through the city.
and towards the east are positive, the west are negative. Or you can say 180 degree east, 180 degree west. Got it? What is latitude? What is 0 degree latitude?
Equator?
Equator. Okay. So similar to latitude and longitude, there is something called right ascension and declination. Okay. So here, right ascension. If you look at it, so where are these latitude and longitudes? Latitude, longitudes are on the surface of Earth. You see that? If you have an orbiting body like this, you cannot really express this as latitude, longitude. You can express this as right ascension and declination. Okay. So right ascension is starting with this. What is this angle? Okay? This is called alpha. You see that? And declination is, this is equator, this angle. Delta. So you can refer figure 4.5 in your text. Okay, you have a copy.
So alpha is the ascension, delta is declination.
Delta is declination, yes. Alpha is ascension and right ascension. You can always think of, so what is this? What would this be? Latitude, longitude wise? This is similar to longitude. Does that make sense? So if Earth is, or
Can you really say that? Because the Earth is inside the rotation. You don't know how it's pitched.
so what is happening is this right ascension, and unlike latitude, what do you know about latitude, longitude of a place? It's constant,
Yeah,
right? Here it is not constant.
yeah, because it's based off the ECI.
It's based off ECI. So Earth, the orbiting body is constantly moving. So you can express this R and V in terms of right ascension and declination. This is important because you know what azimuth and elevation is? From a place, azimuth, elevation. So how do you identify an object in space or when something is moving like this?
You do its direction and its height.
That is elevation. So what you do is, if the space station is going like this, listen, you're too much on the cell phone, okay? If you're going like this, okay, does it have to go like this or it can go like this? Does it have to, if you're tracking in a satellite, okay, like this, does it have to go like this?
Instead of like this.
It can go like this, it can go like this, right?
Yeah.
So it can form that curve. Can it go like this?
Yeah, as long as it's right side.
It can go in any direction, right? So if you look at, this is the azimuth. You see that? So if my hand is like this, the azimuth is 360 degrees. You start from north and you sweep your arm. It will tell you where it is starting. What is the starting azimuth? Elevation is, what is the maximum elevation you can get? So this is elevation.
Even the curve over?
Over. So the flat thing is the azimuth and the curved thing is elevation. These two will help you describe the motion of something which is going over.
What is the first word? Like
Azimuth. A-Z-I-M-U-T-H. Okay. This right ascension is very similar to azimuth. You see, but it is from the center of the earth. So here, what is this? Azimuth and elevation is from the surface. You get it? This is from the center. Does it make sense? So the azimuth and elevation of an orbiting body changes with respect to where you are seeing it from. Right? If you're seeing it from here, it will be different. If you're seeing it from, let's say, even Auburn, or if you go slightly south, it will be again very different. Okay? So this right ascension, alpha, if you are given this R equal to X I plus Y J plus Z K, okay, and B as Cx I plus Vy J K. Does this make sense to you guys?
Yeah.
Okay. These are the, if this is the R, this is the X component, I is the X component, Y is the J or Y component, Z is the K or Z component. Got it? And this is the velocity component. You can use this formula see if this makes sense. Alpha is, or how do you calculate declination? Tell me first, how do you calculate declination? Anybody? Use your basic understanding of sine and cosine. What is sine, or here it is, what is sine delta? Anybody? Is it making sense to you? So this is. Let's continue this next time. Okay? I think it's time. But read up this right ascension and declination. Okay? Please read up it's section 4.3 in the text. Please refer the figure we'll discuss. Azimuth is again an angle.